First of all, I would like to thank the organizer for inviting me here. So here I put a picture of Michigan State. This is how it looks like right now because we just had some first snow of the season. So today I'm going to talk to you about quantum control in quantum dots. Okay, so I will talk about quantum control of excitons and spin systems in quantum dots. So what do I mean by quantum control? So the idea of quantum control is the following. So imagine that you have a very simple quantum system. It could be a quantum dot, it could be a single atom, it could be an impurity in a semiconductor system. And this can be described by an Hamiltonian, and this Hamiltonian will have eigenstates. Okay? So by quantum control, I mean that I would like to build another piece, which is called a control Hamiltonian, and this Hamiltonian depends on time. And with this control Hamiltonian, you want to be able to prepare the quantum state of your system in any arbitrary linear combination of eigenstates, and you want to control as a function of time those coefficients. Okay? So you want the full control of the quantum state. And this is a control problem. It's very similar to what you have in engineering, in classical systems. And in particular, you have a lot of control parameters that you can tune and change and to optimize this control. So my job as a theorist is basically to think about new methods and new schemes to realize this control Hamiltonian. Okay? And after I find those schemes, I also try to optimize the control parameters to get the best control as possible. So today we'll talk about that, and we'll talk about that in the specific case of semiconductor quantum dots. And I will talk about control that is realized using light, so using optics and using lasers, using the optical pulses. And so this is a conference about quantum computing. So this quantum control is very important for quantum computing because, as Vishal explained this morning, so when you have a quantum computer, you have those bits, and then you have quantum gates, and the problem of realizing those quantum gates is basically a control problem. So if we find new efficient way to build those control Hamiltonians, then we have a better chance to realize a quantum computer. Okay? So that's a little bit the motivation. And so I divided this talk in two parts. So in the first part, I will talk about quantum dots that are neutral, so there is no charge in the quantum dots. And first I will give you an overview of those systems, how they're grown, how they look like. And then I will talk about the control using light of excitons. So excitons are basically optical excitations in those dots. And I will show you how you can control the quantum states of excitons using Rkky oscillations. And then in the second part, I'm going to consider charged dots. So in the case of charged dots, you can have one electron on each dot, for instance. And in that case, you have an electron, so you can have a spin. So in the second part, I will talk about the control using light of the spin degrees of freedom for the system. And so I will talk about the control of a single spin that can be realized using Raman control. And I will also talk about the control of two spins, which is important for the realization of quantum gates. And I will talk about two schemes that we developed. One is called optical Rkky, which is inspired by a theory in magnetism, and another one is the quantum, based on the quantum Zeno effect. Okay? So that's the plan. Control of exciton by excitons. So what is an exciton? An exciton is an elementary excitation of is an element of optical elementary excitation of a semiconductor system. And typically we work with semiconductors that have good optical properties, and gallium arsenide is the best example. So those are the bands for gallium arsenide. You have valence band, a conduction band here. So when you shine light, you're going to create, you remove one electron from the valence band, you have a conduction band, you create one electron hole pair. This electron hole pair will propagate in the crystal, and actually, since here you have a positive charge, here a negative charge, you will have a bound state. And this bound state is called an exciton. And this bound state is very similar to an hydrogen system. And in fact, you find basically the same spectrum, except that the characteristic length and the characteristic energies are rescaled because the material has the electric constant that is not the electric constant in the vacuum, and has an effective mass for the carriers which is different than the one for the hydrogen. So the characteristic energies, you have a Bohr radius which is much bigger than the Bohr radius of atoms, and a binding energy which is much smaller. Okay? So those are excitons, and we're gonna use for this control exciton is confined system, and the simplest example is excitons in quantum wells. So it's basically a sandwich of different materials. Gallium arsenide is here in the middle, and you put materials on the side that have a higher gap. So you confine the electrons and the holes in this plane here, and when you create the excitons, those excitons are free to move in this plane. Okay. So this is a quantum well. Actually, I'm talking about quantum well because the easiest way to make a quantum dot is just to take a bad quantum well. Okay? So you take a quantum well, you try to grow a quantum well, and you do it too fast, very fast. And what happens is that at the interface between the material that makes the well and the barrier, you will have fluctuations in the number of atomic planes that are deposited in this structure. This deposition is called MBE deposition. So here, for instance, this island here, you have a larger number of atomic planes in the quantum well. So when you shine light, okay, the electron and the holes, they will prefer to end up in this region because they have a larger barrier, they have a larger well, so they have a lower energy. So, and this is the picture for the quantum well, for the exciton, and it tends to be trapped in the region in which you have a fluctuation in the layer of the quantum well. And those are called interface fluctuation quantum dots. And actually, the first experiments on single dots, they were done already in '96 on this type of structures, okay, which are basically random, accidental quantum dots. Okay, but they are quantum dots. There are other types of dots that have good optical properties, and they're used for the type of applications I'm talking about. And those other types are those self-assembled quantum dots. So in self-assembled quantum dots, you start with a material like gallium arsenide, and then you grow a different type of material. In this case, it's indium arsenide. And this second material has a lattice constant that is smaller than the first one. So when you try to grow one on top of the other, there is a strain that accumulates at the interface here. Actually, there is a layer that is called a weighting layer here. And then at a given point, there is elastic energy that accumulates. At a given point, those atoms collapse and form in a spontaneous way those little pyramids, and those are self-assembled quantum dots. And here you have a picture. This is taken in 2000, and there are, and both those self-assembled and those monolayer fluctuation quantum dots are actually random, so you cannot control the position of the dots. But there are ways now in which you can grow dots in regular arrays, and this is a recent example from a group in Switzerland. And so what you do here, you start with a material, and then you can etch a shape in the sample. Like in this case, they etched pyramids. And then you can grow a different type, in this case is gallium arsenide, and then on the tip of the pyramid, you can form a quantum dot. So there you can get excitons very well localized. And this technique is very well developed, and actually now they can control the position very precisely, and they can also control the emission of the exciton. So they have really an homogeneous system. Okay, so but I'm going back now at those first dots, the interface fluctuation quantum dots. So if you do an optics measurement, you will see those very narrow lines. And those are lines corresponding to the emission of excitons or the absorption of excitons from a single dot. So this is an experiment done on a single dot. And you can see also why those dots are sometimes called artificial hadrons, because you have those peaks are narrow exactly like you would have in an atomic system. Okay? So the density of state is the same as for an atom. And those quantum dots, they also have very peculiar and interesting properties concerning the spin of the exciton. So this is a profile of the band for the dots. Here you have the conduction band, and you have confined levels for the electrons in conduction, and this is the valence band. You also confine the electron in the valence. And in those systems, valence electrons are basically p-like. So they have an angular momentum equal 1, and when you combine with the spin, and you take into account spin orbit, and you take into account the fact that those dots are drawn in this epitaxial way, so you break the symmetry in one direction. So what happens is that the holes here can only have total angular momentum plus or minus 3/2. Okay? So it's coming from the L1 of the angular momentum plus the spin. While the electron is only is a S-type state, so the spin is plus or minus 1/2. So now when you send a photon, the photon also has a spin, okay, and the spin of the photon is determined by the polarization of the light. So if you have a photon that is a sigma minus with respect to the propagation, with respect to the growth direction of the well, then that means that the total spin for this photon is -1. Okay? Because the spin of the photon is 1. So when you project in the sigma minus polarized photon is -1. So that means that if you send us a -1 photon, then you will have a hole which is -3/2 and an electron which is +1/2. While if you send a plus photon, so total spin 1 plus 1, then you have the hole is +3/2 and the electron is -1/2. So you have to conserve the total angular momentum in the optical transition. And this is very important because you can control, using the polarization of the light, you can control which exciton you are making in the dot. Okay? So you have a very important control parameter. And another thing you can do in those quantum dots, you can put more than one electron pair on each dot. Okay? So for instance, you can create first an exciton, and then you send another photon, and you create a system in the dot with 2 electrons and 2 holes. Okay? So if you want to push the analogy with the atomic system, if we say that the exciton is like an hydrogen atom, in the same dot, by adding another photon, you can have basically a system which looks like a helium, right? Which you have 2 protons and 2 electrons. Here you have 2 holes and 2 electrons. And so there is a nice many-body physics that develops in those systems as when you start to add photons. And those biexcitons can be seen. It's a little bit harder to see than excitons because you first need to create an exciton, and then you need to send a second pulse. So like here. So first you send. So if you only do a measurement, you only see exciton peaks. But if you do an excitation of an exciton first, and then you send another pulse, then you see the biexciton. Okay? And this everything in one dot. And you can also charge the dots, and to do that, you do you use some devices like that in which you have an external gate, and you have dots, and you have a back contact here. So changing the gate, you can take electrons from the Fermi energy here and inject electrons in your dot. So if you do on the same dot, you can look at the properties when the dot is neutral, and you will find excitons. You can change the voltage and charge the exciton, charge the dot, and you have a different emission. And this emission corresponds to the emission from an object that has 2 electrons and 1 hole, okay, because we charge this dot with 1 electron. And an object with 2 electrons and 1 hole is called a trion. Okay? And you can even put 2 electrons and you will have an electron with -2. Okay, so this is, so how can we do this control? Basically, we have many options for this control. We can do the control in neutral dots, and for instance, we could take a wave function that has to do with a dot that is completely empty, so that's a vacuum. Or you could have a dot that is coming from this sigma plus polarized light. Okay, so it's a dot, it's an exciton with spin +1, or you can have an exciton with spin -1, or you can have a bi-exciton in the same dot. Okay, and you can do this using Rabi rotations. And I will show you those Rabi rotations. And another possibility is to have, I mean, if you want to still have 4 levels, you can have 2 dots, and then the 2 dots are charged. You want to control the state of a wave function like this, in which you have the 4 possible configuration for the spins. And this can be achieved also with optics, but with different schemes. One is the Raman control for the single spin, and there are also schemes for controlling the interaction between the two. So you need also the 2 spin interaction. So Rabi oscillation. So what does it mean? What is this Rabi oscillation? If we have a 2-level system, like in this case, we can have an empty dot or a dot with 1 exciton. That's a 2-level system. And if you send a laser that is resonant with this transition, and then you look at the probability to find the exciton in the dot, you will see that this probability oscillates as a function of time. Okay? This probability, the frequency of oscillation depends on the dipole moment for the optical transitions and on the amplitude of the electric field in the laser. And this is called the Rabi energy, and this is the Rabi oscillation. So if you send a CW laser, a continuous laser, you see those oscillations. If you send a pulse, and in this pulse you have a frequency that oscillates very fast, and again it's resonant with this, but you have an envelope for the electric field. You can show that basically at the end of the pulse you act to this 2-level system like as a rotation, like when you rotate a spin. Okay, so that's basically how you can do the single exciton rotation, and this has been implemented in a single dot already in 2001 by a group in University of Michigan. And to look at this, basically you have to do an experiment that is called pump and probe. So you first send this pump that makes the rotation. So in this case, the pump is resonant with this plus exciton. So depending on this, you rotate the state between the ground state here and this +1 exciton. And then you send a probe, and this probe is probing the orthogonal transition from the ground state to this minus exciton. So if you invert the population here, the probe will not absorb, so you have an increase in the transmission probability. Okay? So here you put your detector, so you measure the transmission through this quantum dot. And so then you can do that as a function of the delay between the pump and the probe. Okay? So the probe is very narrow in time. And this is an example of this is the differential transmission. So you want to see with the pump and without the pump, and you see the difference. So in this case, this is a pi pulse. So that means that you really create 1 exciton in this dot. Then when you go and probe with the minus, you will see that here you have the maximum reduction of the maximum increase in the transmission. Okay, so you have a peak here. This is a pi pulse. And then of course everything decays because the exciton doesn't like to stay there forever. It will decay by spontaneously emission of a photon. Okay? And then if you do instead a 2 pi, so you do a complete rotation, you see that when you send the probe, you see here, you see the same thing as before. So you really do the complete radio oscillation here. And in the same way, you can look at those oscillations by fixing the delay and changing the amplitude of the field, because remember I told you that the frequency, this radio frequency, depends on the intensity, on the area of the path. So if you change the area by changing the intensity of the field, you also see oscillations. Okay, so this is the oscillation for ground state to exciton transition. But if you want to have the full control of those 4 states, then you also need to show that you can do control of biexcitons, right? So that's a little bit harder, but you can do it, and this is an experiment where this was done. So you basically pump, you have first to pump the exciton, and then you do a pump and probe experiment between the exciton and the biexciton transition. And it's like before here, if you pump the exciton first, and then from the exciton you completely move your population to the biexciton, like here, then you see this maximum in the change of the transmission. Okay? And again, you can look at this as a function fixing the delay and as a function of the intensity of the laser. Okay, so now this is basically a simple example of quantum control in a 4-level system, in a semiconductor system. And the idea is that you can think about this as a very simple quantum computer, okay? Because you have those 2 excitons that are independent, because you can decide if you want to act on the exciton plus or the exciton minus depending on the polarization of the light. So you can say, when I use minus polarized light, then this is my qubit number 1. If I use sigma plus polarized light, I'm looking at qubit number 2, and then basically you can map these 4 states of the ground state, 1 exciton with minus polarization, 1 exciton with plus polarization, and the biexciton to the computational space of 2 qubits. Okay? So if you can do this, you can also. So this is a quantum computer with 2 bits, and this system is not a scalable system because I cannot put more and more bits in the same dot, but we can use this to check some control issues, to check some optimization methods to get this quantum control. And this was done here in the simulation. Basically here, so that was a particular algorithm implemented with optical pulses and excitons in a single dot, and basically using an optimization on the shape of the optical pulse that you use, we show that actually you can reduce the time that you need for the computation by a factor of 10. Okay? So everything has to do with how you mix the colors when you do the optimization. So, okay, so that's an example of optimization, theoretical optimization for the quantum control. And okay, now I want to talk about the case of dots in which you have a spin. And the motivation is that in those exciton-based schemes, you always have that limitation of the final lifetime for the exciton. When you put an exciton in the dot, you always have this probability of recombination by emitting a photon. So the lifetime and the coherence time for those qubits is of the order most of a nanosecond. Okay? While if you could encode your bits in the spin of an electron in the dot, then the coherence time is much longer. Okay? It could be the order of milliseconds. So that's the motivation for working with charged dots instead of neutral dots. And so, okay, that was the scheme for neutral dots. And so for quantum dots, now we start with a system in which there is already an electron in conduction band, but still I want to use light to control the spin. I still want to do quantum control using light. Okay, and to do that, I need to use the selection rules that we talked about for the spin. Now for those tryons, the selection rules are slightly different. So, so here we have a spin in conduction band, and we said we can have either spin down or spin up. And let's say now we send a photon that has a total spin -1. So we said -1 corresponds to an electron up and the hole down. Okay, so in this case, if I send a -1 photon, I can absorb the photon and create a trion. In this case, I already have an electron up, so if I try to send a photon that will create another electron up here, that's going to be blocked by Pauli. I cannot have two electrons here with the same spin. So in this case, the dot is going to be transparent. Okay? So depending on the electron, the state of the spin of the electron in the dot, I have different optical properties. And you can use that to actually implement a rotation for the spin state. Okay? So rotation for the spin state can be done in this way. So that those are the two possible states for the spin. We say it can be down or up. And then if you send this sigma minus polarized light, you couple only this spin down state. Okay? When you couple this spin down state, you send this laser, and this laser, the best way to realize this is to have a laser that is slightly detuned with respect to this trion energy. And at the end of the pulse, you will find that this state with the spin down will acquire a phase, while if you have a spin up, since this one, in this case, the dot is transparent, will remain the same. Okay? So this is equivalent to a rotation around the z-axis for the spin. So you only have a phase in one state. And if you generalize this idea and you apply a transversal magnetic field in the x-axis, and you have those selection rules that are always with respect to the z-axis, which is the growth axis for the system. If you use two lasers, you can show actually that you can realize any arbitrary rotation of this spin state using a laser. And this is basically a Raman scheme. Okay? It's a Raman control scheme. And so this was studied in theory 2004, and basically last year there were the first experiments on proving this control of a single spin in a single dot using light. And there were two experiments. One was U of M again, and another one UC Santa Barbara. And again, those are all pump and probe experiments, and they look at the evolution of the rotation between those two states here induced by light. Okay. And so everything I told you so far for the spin, that was for a system in which you wanted to control only a single spin. But of course, if you want to scale and make a quantum computer, you have to learn how to do gates involving two qubits. So we have to find a way to induce interaction between the spin. Okay? And there are basically two classes of mechanisms that can lead to an interaction between the spin. The simplest one is direct interaction. And direct interaction will be, like in this case, if you have two dots, you have two electrons in the two dots, and you have an overlap of the wave function. Okay? If you have an overlap of the wave function, then you're going to have an exchange interaction between the spin. But there is also another possible strategy, which is the strategy of indirect interactions. In indirect interactions, you have two spins, and in principle, those two spins, they don't have a direct interaction between them, but in this case, they are sitting in a Fermi sea of electrons. And there is a mechanism in theory of magnetism, which is called the Rkky mechanism. This stands for Ruderman, Kittel, Kazuya, Yoshida, the theorists that invented this interaction. And basically, in this case, the interaction between those two spins is mediated by those carriers. So you have an indirect coupling. And there are other examples, but this is Rkky is the most famous. And you can try to get inspired by this indirect interaction, and we try to do an optical version of this Rkky interaction. We call that Rkky, optical Rkky. And the idea here is that if you have those two electrons in two dots and they're far away, so there is no direct overlap of the wave function, what you can do, you can shine light and create excitons or electron hole pairs here in the material that hosts those dots. And the exciton, this is the dashed line that corresponds to the energy of free excitons in this plane. They will couple and they create new particles, and those particles are called polaritons. So right now those polaritons are very popular, so there's a lot of research on polaritons because basically those are bosons, and they're bosons that have a very, very small mass. Okay? And the nice property of those polaritons is that if I take this state here, close to k equals 0, the state is still a 50-50 mixture of electron and hole and photon. So there is a strong matter component, but it behaves like a particle with a mass that is as a mass of a photon in a cavity. So it's probably the lightest particle that you can think about because it's more like a photon, but it's as a mass, okay? As a charge, as electron and holes, not charge, but it can, in particular, it can interact with dots, okay, because it has the electrons. So if you use those, I don't know why. Okay, this is mathematical. So if you use those polaritons, basically you can show that this this indirect coupling between the spin can get a very long range. Okay, so this is the strength of the interaction as a function of the distance between the two quantum dots, and when it's mediated by polariton, here you get that you have a very you can reach distances that are of the order of the fraction of the micron, which is very, very long, and this has to do with these coherent properties of those polaritons that have a very long range. Okay, so so this is that was a method for coupling spins and realizing gates, actually. So now I want to talk to you about another method to induce effectively to realize a gate between two spins in two quantum dots. And this is based on the idea of the quantum Zeno effect. Okay, so what is this quantum Zeno effect? This is a picture of Zeno. So Zeno was a philosopher in the 5th century BC. So he was living in Italy, southern part of Italy, south of Naples. And he was obsessed by the idea of movement. So he was saying, if you have an arrow and you strike the arrow, and if you go, this arrow has to go from point A to point B, before reaching point B, has to get at the midpoint. Okay, but you say, okay, before getting at the midpoint, has to get at the midpoint of the midpoint, that's 1/4. Before getting that, has to get to the 1/8, and so on. So his idea in the 5th century BC was that, okay, then that the arrow cannot move. Okay, so he was saying everything is static, nothing moves, and that was the paradox in ancient times. But in the 70s, Sudarshan and Mishra, they got inspired by this paradox, and they started to think about the equivalent of this Zeno paradox in quantum mechanics. So what is this quantum version of the Zeno effect? So let's say you have here this quantum dot, and this dot can have the ground state, which is empty, or level 2 is one exciton in the dot, and you drive this dot with a resonant electromagnetic field. In that case, you're going to have those coherent radio oscillations that you've seen actually in the experiment that time. So, but now let's say we put a detector here on the dot. Okay, we want to go and check, is the exciton there or not? Is the exciton there or not? And we want to do that very fast. Okay, so a very fast detector. If you do that, then let's say you start with your radio oscillation, and then you go and measure the probability to find the exciton there. And if this measurement is very fast, basically the probability to find the exciton here is going to be very small. Okay? So the probability to find the exciton in the excited state is going to be nearly 0, and the probability would be nearly close to 1 to find the exciton in the ground state. So, but after you measure, then your state will collapse, right? Because you measure that the probability to have an exciton is nearly 0, and then you reset your quantum state to 0, because if you measure that there is no exciton, you reset your dot to the ground state. So basically, the idea is that if you have a rapid set of measurements on this excited state, and the speed of those measurements is much faster than this rapid oscillation time, okay, then basically your system does not evolve. Your system remains frozen in this ground state, because every time you try to go up, you measure, and then you collapse to the ground state. So, and actually in quantum mechanics, you don't really need to measure the thing. You only need to have something that in principle can extract the information of having the exciton there or not. In particular, you can replace this detector with a system like that, in which you have that this excited state here can emit with a very high probability a phonon, okay, and decay to another state. Okay? So basically this dissipation channel, this bath channel, is equivalent to a measurement. Okay? And the idea is that if you emit a phonon, then in principle you can go and detect if the phonon is there. It doesn't matter that you look at the phonon or not, it's that in principle you can do it, that's equivalent, therefore that's equivalent to a measurement. Okay, and this is the idea, and what we have done, we try to use that to realize a gate in a system of two dots. Okay? And the scheme is clever, it's a little bit complicated, but the idea is that you have 3 dots. Again, we said we have 2 dots that are charged, so we have the spin on each dot, that this is the those are, if you want, those are the qubits that we want to use for a gate, and then we have a central dot that is neutral. Okay. So the energy scheme is something like that. Here you have the central dot has a ground state and has an exciton energy here, and the 2 lateral dots they can have a spin, okay, and the spin can be down or up, and then you have this trion state here that corresponds to a system with 2 electrons and 2 holes. Okay? And you have to engineer your system in such a way that the
2 more minutes.
Okay, I'm done. Yeah, in such a way that the energy levels are like that. So let's see what happened. Now we send sigma. Oh, that should be a sigma minus polarized light. So that means that the spin of the photon is -1. Okay, so we said the spin of the photon is -1. What you can create here are always exciton with electron up and hole down. So if here you have an electron down, okay, then when you create this exciton can decay by phonon emission to one of the 2 lateral dots. So in this case, you have 2 channels for dissipation that are open. Now, if you flip the spin of your bit, or your qubit, then you can shut down one of the channels, like in this case, because if I flip up the electron here I have my exciton. Here I already have an exciton up, so I cannot have 2 electrons and 1 hole, 2 electrons with the same spin. So you block a channel depending on the quantum state of your qubit. But still, in this case, okay, you still have the quantum zone on the other side. So this state will still remain frozen if you try to realize a rapid rotation. It's the same thing here. This is the same as this. So the only case in which you'll be able to do a full rapid rotation would be if you shut down both channels. If you close both channels to this dissipation, then you are free to have a full rapid rotation, and then you have, if you have a full rapid rotation, basically you get a minus sign when you look at what happens to the wave function. So And this is what happened to the state of the 2 bits, 2 spins, and this is a fundamental quantum gate, and you can use this actually for quantum computing. I think Vishal today he talked. Actually, you can transform this in a control knot gate. Okay, that's it. So you can calculate actually the fidelity, and you can show that the fidelity is for this operation is good, and actually that if you have more dissipation, more stronger coupling with phonons, you get something that works better, which is actually counterintuitive in the quantum computing business. So, okay, I'm done. So I talked about control of excitons and biexitons in a single dot using light, using Rkky oscillations. I talked about the control of 1 spin using those Raman transitions and 2 spins. For 2 spins, I gave you 2 theoretical ideas on how to make basically a gate using light. Okay. Thank you very much.